Okay, we're gonna see if this works. We've been having some problems with video quality with the live streaming being uploaded, so I wanted to try and do a pre-recorded instead and see how that goes. We may have to switch for the rest of the semester or until I find a better streaming system. Real quick before we get into our topic this week, which is plate tectonics. Your exam is next week. It is going to be open for 48 hours, so from Monday, midnight Monday until 11:59 p.m. on Tuesday. During that 48 hours, you need to find a 2-hour time span where you can sit down and take the test. You have to do it all in one sitting. You can't come back to it. If for some reason you cannot take it on Monday or Tuesday, I need you to contact me right away. I can try and make it so you might be able to take it Sunday evening or Wednesday morning, but I really can't move it more than that, just because the more time I allow, the longer people have to share answers. And while I would love to trust all of you, I really just cannot be too cautious with that. Additionally, on Wednesday, we're going to be starting the next chapter of material, so I really want to make sure that people are getting the test done and ready to move on with the next topic as soon as possible. So keep that in mind. If you need to schedule a different exam time, let me know. Otherwise, anytime Monday or Tuesday when you have 2 hours, sit down, take the test. Okay, moving on. This week we are talking about plate tectonics. This is basically the driving theory behind many concepts in geology. So plate tectonics theory provides a comprehensive explanation for the current Earth's surface and how it came to be and what forces are shaping it. Okay. Plate tectonics helps us explain how ocean basins have formed, how the continents have formed, the formation of mountain ranges, the current distribution of earthquakes and volcanoes, the types and locations of fault systems within the Earth, and the location and size of oceans and continents in geologic time, and the distribution of life on Earth in geologic time. So if you remember back in the introductory of your textbook, we talked about the composition of the Earth. So the Earth is made up, if you cut it in half, of a variety of layers. We've got the crust, which is about 5 to 70 kilometers thick, basically from where we're standing down into the Earth. Beneath that is the mantle. You have your rigid upper mantle, and then you have your less rigid inner mantle. Okay, and if you look at the zoom in right here, you can see we have our crust here, and beneath that we have our asthenosphere, or sorry, we have our lithosphere and then the asthenosphere. Then we have our molten outer core and our solid inner core. So the plate tectonics theory states that tectonic plates are pieces of rigid lithosphere, which includes the crust, that float on top of a plastic or weaker asthenosphere. So lithosphere is a rigid outer layer of the Earth, which includes the crust and the upper mantle. The asthenosphere is a zone of weaker material in the upper mantle, immediately below the lithosphere. Imagine the asthenosphere being similar to Play-Doh, where if you pushed your finger into it, it would compress down. Or like the Tempur-Pedic beds, I guess. You pushed your hand and it would press down, but if you moved your hand, it would kind of bounce back up. And large-scale geologic features occur at plate boundaries. So this just gives you a better breakdown of the composition of the Earth. This is looking at a worldwide distribution of earthquakes. Here they're not segregated on magnitude or depth. This is just a pinpoint for every earthquake occurrence over, I think it's over a 5-year time span. But if you look, earthquake activity actually mirrors plate boundaries. So here we've got your Pacific plate. We've got earthquakes all around the outer edge. We've got our Caribbean plate. So you notice these earthquakes, with exceptions of earthquakes within the interiors of plates, primarily they occur right at these boundary lines. So your Pacific plate, your Nazca plate, your South American, your Caribbean, and there's actually a North American plate, Eurasian. So plate tectonics is driven by the heat generated in the Earth's interior. So the Earth's interior heat actually causes a release of kinetic energy that moves through the solid, liquids, and gas in the core and the mantle and the crust. Let's go back to that. So if you imagine if you put a pot of water, like a glass pot, on the stove to boil, and if you watch, the water will heat up and rise, and as it cools, it goes to the outsides and back down. So it moves in a convection motion. Well, the same kind of thing happens within the materials within the Earth. And as it does that, it actually causes that movement of plate boundaries as it comes up and starts to spread out. This is where we get those mid-ocean ridges or divergent boundaries. And then where it starts to cool down and drop again, that's where we get the subduction zones, which we'll talk more about later. So what are Earth's internal heat sources? So we've got radioactive decay, residual heat from the Earth's formation, and internal friction sources. So the primary one that really drives this is the radioactive decay of the elements within the Earth's mantle and core. So what are global effects of Earth's internal heat engine? And this is where we start to talk about it. So the youngest ocean crust is found along the parts of the ocean that are bathymetrically high, or the shallowest regions. As ocean crust gets older, as you travel perpendicularly. Ocean crust older than 180 million years has disappeared. Okay, so the oldest crust is associated with these oceanic trenches. So here we're looking at a cross-section of the Earth. So the youngest ocean crust is found at these mid-ocean regions. So like I talked about, the hot material rises, and as it rises, it tries to break through the crust, and this is where the crust separates, and you get creation of new material. And as they start to separate, you push the older material away from that zone of young crust, or that mid-ocean ridge. And oceanic crust is less dense when it's hot. So the material here is very, very hot, so it has a much lower density. As the material cools, the density starts to increase, so that material starts to sink down and settle down, which is why you get a bathymetric high here and bathymetric lows this way, until it reaches another plate. And when these two plates collide, the older oceanic crust will subduct under the younger oceanic crust because the older material is more dense, and it will go down, and the younger material will ride above it. So this is where you get a subduction zone, and you have one plate dropping beneath the other. And as this plate subducts, it starts to warm up and it starts to remelt. And because of the gases trapped in it from being exposed to their surface, then you can get rising of the molten material here, which is where you get the development of volcanic arcs. As this plate subducts and melts, some of the material comes back up, breaks through the crust, and volcanic activity. Here is an example where the oceanic crust is denser than continental crust. So if you remember, oceanic crust tends to be more basaltic in composition, whereas continental crust is more mafic, or felsic in composition. Oceanic crust is more mafic. So because the oceanic crust is more mafic, it's got more of that iron, the magnesium, or iron and manganese, so it is denser, so it will sink below the continental crust. As it sinks below, again, that remelting will actually cause volcanic activity along the edge of that continental plate. This is why you get a lot of volcanoes and volcanic activity along the western edge of South America, because you have an oceanic plate subducting beneath a continental plate. So the subduction zones are ocean basin trenches, where the crust is transported back into the mantle and destroyed by remelting. Most volcanic trends are located outboard of the direction of the subduction. So when we talk about volcanic activity, they mirror plate boundaries, but they're not on the boundary. Okay? They are set a certain amount of distance in from that subduction zone because they are actually located above where this remelting occurs and the material forces itself back to the surface. So it doesn't occur right here. It occurs some kilometers into the overriding plate. So plate tectonics release heat from the Earth's interior towards the surface. And the heat flow is high at ridges and low at subduction zones because the heat is escaping the Earth's interior here, and the material is cooling and dropping back down in to be reheated here. So you have much higher temperatures here than you do here. So describe how a convection cell works. And I already gave you an example. So what kind of other examples do we see? So the pan of boiling liquid, I already showed you that. In the hydrologic cycle, this is actually a very large-scale convection cycle. You have water evaporating off the surface. It condenses. It is then transported away from where it evaporated. It precipitates down. It runs back into an ocean or lake and evaporates again. So this is a very large-scale convection cell. And then in the mantle of the Earth, however, it is important to note that the convection that occurs within the Earth is assumed based on data we've collected at the Earth's surface that indicate it's a convection cell, but we have not been able to directly observe that this is the case. So along with volcanoes, earthquakes also mirror the plate boundaries. And this is because you have your spreading zones like we talked about, so the mid-ocean ridges, and these plates, as they move apart, they don't move apart uniform the whole way. So as they pull apart, they kind of rub up against each other and shift. And then in your subduction zones, you've got two plates coming together, and there's a lot of friction if you've got one dropping down underneath the other, which will cause tremors within the Earth. So when you look here, you have your mid-ocean ridges here that tend to have lower scale kind of earthquake activity, and then your subduction zones, which tend to be the more violent ones. These numbers here indicate your spreading rate in centimeters per year. So the mid-ocean ridge closest to North America spreads at about 2.5 centimeters a year in either direction. Whereas if you go off the west coast, just off of Mexico and Central America, we have a much higher rate of about 10 centimeters per year. So these arrows are just showing the spreading directions, and the apex of the triangle shows the subduction directions. So these plates are spreading outwards this way. This is a continental plate and is much less dense than the oceanic, right? So the Nazca plate is hitting this continental region and subducting beneath it. So this arrow is pointing, saying that this plate is subducting into this one. Okay. It's also important to note that the Indo-Australian plate is actually in the process of developing a split and breaking into two plates. Okay, so they're actually starting to divide apart there. So, is the Pacific Ocean getting bigger or smaller, and why? Okay, if you remember from the last slide, the North American and South American plates in the Eurasian and Arabians are only spreading at a rate of 1.6 to 3.5 per year. Whereas if you look along the Pacific plate, we have a spreading rate of 6 to 16.5 centimeters per year. So the Pacific plate is spreading at a much higher rate than the North American plate. So that would indicate that the Pacific Ocean is actually getting larger. Okay, like I stated, oceanic crust is denser than continental crust. So new oceanic crust is what's created at mid-ocean ridges. These are known as spreading centers because they spread the crust in opposite directions along the ridges. The plate boundaries along these are divergent plate boundaries and are the location of shallow earthquakes. Oceanic crust is destroyed by subduction into the trenches. These are subduction zones, and which are convergent boundaries. Subduction zones require one or more plate to consist of oceanic crust. When oceanic crust is subducted or overridden, it remelts, and this movement into the mantle pulls younger crust after it. The remelted crust will ascend and create volcanoes as the hot magma ascends to the surface through fractures in the Earth's crust and pour out as lava. So the Earth is constantly recycling oceanic crust through convection and gravity. The continents on each planet continually move away from the spreading centers as passive passengers, except where continents are currently being rifted apart. So for the most part, these spreading or divergent zones occur in the ocean. However, there are a few divergent zones that actually exist on continents, and these are typically classified as rift zones or rift valleys. Oops. And I will talk about one of those in a little bit. So plate tectonics control the movement and the shape of continents and oceans over time. So we talked about the convection or convective currents of heat that drive the plate tectonic process. Convection exists when fluids are heated, become less dense, and rise, so that magma is becoming less dense as it warms up, and then as it cools, it becomes more dense and sinks again. So you can see the associated seismic activity associated with this. Let's see if I can get a bigger image of this. So this is a good example of the South American plate. This is, I forget if it's Chile or Argentina, along the edge with the Andes Mountains. But you've got the Nazca plate colliding with the South American plate and then subducting. Okay, so you have your initial earthquake activity occurring right where the plates come together. And then you'll have more as the friction increases along the plate boundaries here. So this is just showing earthquake intensity with depth. So you're going to have much stronger earthquakes along here with an increase in intensity as you go deeper. Or sorry, a decrease in intensity as you go deeper. So there are three types of plate boundaries. We already talked a bit about the divergent and the convergent. The third is a transform plate boundary. So let's go deeper into the divergent. Like I said, these are where plates move apart. Mid-ocean ridges begin as rift valleys. So I talked about the fact that there are currently a few rift valleys that are located on continents. So the continent of Africa is actually in the process of being split apart by the Great African Rift Valley. It runs through Kenya and Tanzania and is actually dividing that continent in two. As this rift valley continues to spread, it thins that crust layer, allowing for increased volcanic activity and magma activity. But as it does this, it also starts to create a regional topographic low. And once you reach a certain elevation, you start to get an influx of brackish or seawater. That's actually how the Red Sea was created. It was from a rift valley that originally started within a continent. So as they pull apart, they have a lot of volcanic activity, which is more mafic in composition, so it's much more dense, giving you a new creation of seafloor. You tend to get shallow focused earthquakes here because it's a lot of activity right at the Earth's surface. So this is showing you the creation of a rift valley. So you have a heat source forcing upward, and it creates an upwarped area of lower density crust. So you see it starts to fracture it and have minor breakthroughs. As it fractures it apart, it forces the crust outward and starts to create this rift. So you start to get this pushing away of the continental material, and the more mafic magma starts to accumulate in the base here. Further spreading starts to create a narrow sea like the Red Sea. So you have it where it's reaching a low enough elevation that fills up with water, until eventually it spreads wide enough that it actually creates an ocean basin and is now fully separated land masses. Okay, so you can see here it's starting, still a little connected. There's potential that it's still connected by continental material here, but once it is divided far enough where there is no continental crust coming into contact at all, that's when you've started to create a sea and an ocean basin. So this is just showing you a divergent boundary of the South American plate and the African plate. Oops. And you've got your oceanic lithosphere. So you see how your younger material is a slightly higher elevation, and as you go further away from that divergent boundary, it actually drops. So you go from about 2 kilometers below sea level to 5 kilometers below sea level here. you've got the same going on here. This just shows how as the material cools and moves further away, it actually drops in elevation. Sorry, guys. So convergent boundaries are when plates move towards each other. Oceanic crust is destroyed, oceanic crust is destroyed, creating an oceanic trench, which is this topographic low as it drops down, and a volcanic arc. So you get the oceanic trench up against a continental crust, or you can get an oceanic trench where it then creates an island arc. You tend to get deep focus earthquakes associated with these. So you have earthquakes that are occurring down here within the Earth's interior because of that dropping plate, because of the melting of the materials and the release of gases. There are three types of convergent plate boundaries. You have ocean-continent, which we see right here. We have ocean-ocean, and we can have continent-continent. So ocean-continent conversion is where oceanic plate is subducted. This is where continental arcs are typically generated, and these are classified by explosive volcanic eruptions, lots of volcanic activity, such as the western coast of South America. We still get a lot of volcanic and magmatic activity, a lot of earthquakes along that region, and the formation of mountain ranges due to this volcanic activity. So we look at this image, and these are color indicators for the depths of earthquakes. So the very shallow ones are red, then yellow, green, and the blue are the deepest. So what direction is subduction heading here? Okay, so here, the shallow ones are where the plates first meet, and then the blue ones are where there is one plate beneath the other at depth, and that would indicate that this one is going underneath this one, correct? Because it drops down, and as it's dropping down, it's still releasing energy up within the interior of the continent. So here, it's the opposite, right? This plate is subducting under this plate because of the same thing. With oceanic to oceanic convergent, the denser plate is subducted. So like I said, as the material cools, it increases in density. So typically, the older oceanic material would subduct beneath the younger. The deep trenches are then generated. You get a trench where one starts to drop beneath the other, and you get a creation of volcanic island arcs. A good example is the Aleutian Island chain in Alaska. These are islands that are created by an essentially stationary plate boundary, so they maintain their position within their plate. They're due to the subduction of a different plate. And finally, continent to continent conversion. So continental crust is much less dense than oceanic crust or magma. So you don't get a subduction of continental crust, but what happens is one crust will override the other, so it'll just shove itself up over the other one. This occurs when continents collide after closing an ocean basin. So this is where if North America started shoving towards Europe, and we would just start to, close that basin and squeeze England between us before one shoved over the other. So continental crust collides, folds, and deforms. This is how we get mountain ranges. A good example of a historic mountain range are the Appalachian Mountains. These are the collision of North America with several land masses and its collision with Africa before opening the present Atlantic Ocean. A good, active evidence of continental collision is the Himalayan mountains. There is actually continual collision. The Indian continent is actually actively colliding with the Asian continent. And the Himalayas are actually growing at a significant rate every year. The mountains are building up, and they're also spreading outwards because of this collision. So this is a very active process on the Earth still. So here we're just looking at the collision of India with Eurasia, and as it moves towards it, it starts to close this ocean basin. And as it collides with it, it just starts to push this, this crust from the Eurasia plate up over the Indian plate. So the Indian plate's getting forced down beneath it a bit, but it's being added to that material that's really shoving these Himalayan mountains up. So this just shows you the trajectory of India over the past 71 million years to start creating the Himalayas. Finally, transform boundaries. These are where plates actually slide past one another. They occur along all the mid-ocean ridges and some plate boundaries. The San Andreas Fault marks a well-known transform boundary between the Pacific and North American plates. So, we'll get into that. So what happens on a transform boundary is plate segments slide past one another. They fracture perpendicular to mid-ocean ridges, which allow for different rates of spreading along these ridge systems. They create very shallow but very strong earthquakes. So what happens here is if you have a mid-ocean ridge or a rift valley, the plates don't always spread out at an even rate. So as they spread, you can actually get disjoined sections where they offset from one another. So you'll have your mid-ocean ridge spreading, but as the plates pull apart, it's kind of like if you had your fingers like this, they don't pull apart evenly, so one might pull apart faster than the other. So there's additional seafloor evidence which support the theory of plate tectonics. So seafloor sediment thickness occurs or increases away from the mid-ocean ridges. So what this would indicate is that there's very little, okay, let's back up. So remember we talked about rocks. If you have a rock that weathers and breaks down into sediment and it's carried downstream, and like we said, a lot of times it ends up in the ocean. Well, if you're always depositing this material into the ocean, it starts building up layers, right? But when we reach the mid-ocean ridges, there's little to no sediment layers on top of the crust, which would indicate that it has not existed long enough for that material to accumulate. But the further you go, the thicker that sediment layer becomes, indicating that more and more sediment has had the chance to be carried off the continent into the ocean and settle there, which would indicate that you get a younger to older sequence of the seafloor. There are some other clues we have, such as hotspots. These are intraplate features, so they're a feature within the plate. You saw some of the dots of the earthquakes or volcanoes that were not associated with a plate boundary. These hotspots are areas of intense volcanic activity, and these hotspots remain in the same place over a long period of time. Volcanic island trends form above these hotspots. So, for instance, the Pacific Ocean hotspot. This is an area where a rising mantle plume has broken through the crust. We get an area of active heating of the mantle, so it's a small portion that is hotter than the rest and breaks through the crust. And the crust has traveled over that hot spot, and as it has, over the millions of years, it has actually created island chains through the volcanic activity. So the Hawaiian Islands, we have our oldest island at 5.6 million years old up to the northwest. And as we go southeast down to present Hawaii, this is where we still have very active current volcanic activity, which would indicate that this hot spot right here is what created this island chain, and as the Pacific plate was moving, it was dragging it over and resting for however periods of time, which created the new Hawaiian Islands. Same with the Emperor Seamount chain. There's a hot spot that has also created those islands. So these hot spots are not associated with mid-ocean ridges. Okay, they're just an area of higher temperature, higher velocity that have no relation to the actual breakthrough and very constant driven spreading of these different plates. It's a hot region underneath the plate which breaks through to create these islands but does not drive this convective process. Okay, so I'm going to post the link to this YouTube video. It's just talking about Hawaii's hotspot. And then this is just looking at the global hotspot locations today. So if we're looking here, this is where the Hawaiian hotspot is currently located. Yellowstone is actually over a hotspot, which is why we have those geysers and the hot springs occurring there currently. That's a region of higher temperature crust material beneath the surface. And while it is not causing any sort of active volcanic activity today, it is causing active geothermal process. The Canary Islands have some hot spots. There's significant hot spots within the continent of Africa. And this is a video just discussing more on the theory of plate tectonics with some footage of some really good real-life examples. I'll post that link too. It is about a 16-minute video, so keep that in mind. And then Mother Earth Loves Drama. It's an old movie poster. She was a tectonic plate. He was several thousand cubic miles of boiling magma. Together they move a nation. So, okay, that is the end of that. Real quick, I want to talk to you about one more thing. See if I can. Hold on a second. Okay. So I'm going to post this. Oops, I'm going to post this for you all. This is something that I use for my lab in my in-class lessons, but it's very difficult to do the lab with you all. So this is just discussing some maps looking at the relationship between plate tectonics and volcanoes and earthquakes. So there's going to be some teacher's notes on here that I would like you to look at. So first it just discusses the plate boundaries, and then it compares, there we go, it compares the plate boundaries to areas of active earthquakes. And then it goes on to talk about the types of boundaries and the intensity of earthquakes. And when I post it, it's going to post in a PowerPoint. There's all kinds, here, I'll show you. It's, yeah, there's all kinds of notes down here associated with each slide that I want you to look at. So then it, oh sorry, that was the volcano. So then it looks at the earthquakes and its relationship to the plate boundaries. Okay, and then finally we start to look at geochronology, so age of rocks. So the younger material is red and the older material is blue. And just taking a look at how this all relates, it gives a better visual of the relationship between, you know, the age of the rock, the age of the oceanic crust, from the mid-ocean ridges to the subduction zones, and how it relates to volcanic activity and earthquake activity. So just take a look at this. I'm not going to test you on any of it, but it's a really good kind of secondary set of information. So I'm going to post that for you guys. I'm going to post a link to the 2 videos. If you have any questions on any of the material before your exam next week, shoot me an email, let me know. And otherwise, that is it. I hope you all have a good week.